Hello friends, welcome. So here we would discuss, in this class we would discuss what is partial derivative. So the reason for discussing partial derivative and why you should know it is because sometimes in physics, if we have this tool in our hand, similar to the differentiation, it's a tool in our hand. So if we know this tool, the partial derivative, partial differentiation, if we know this, then our problems sometimes in physics, the numerical problems, they become much simpler. So in this class we would understand what is partial derivative, and in subsequent class, in the very next class, we will see its application in error propagation. So error propagation is a topic which we need to study, which is there in our syllabus. So we will just use this tool to understand how our problems become very simple if we know partial derivatives. The error propagation problems become very simple. So let's just start with a very simple example. So this is the volume of a cone, and we all know that it is given by this formula. It is one third of pi r squared h. So here the thing is, if v is a function of both r and h, so we can write it like this: v is a function of both r and h. So if that is the case, 1 by 3 pi r squared h. So v is a function of both r and h, and we have to explicitly mention that. We are saying that v varies with both r and h. So there are two variables in this equation. It is not only r and not only h. Both of them are vary. We can change both. So if we take the derivative of, this is the complete derivative, okay? This is the complete derivative of dv by dh. So with respect to height, okay? So what would that come out to be? First we'll differentiate dh. See, these two are in multiplication. So the first term would be, so this is normal derivative. We're just taking the derivative. We're just doing the differentiation. So first we'll differentiate this entire term with respect to h. Okay, so this h we will differentiate, and this h would just vanish because the differentiation of h raised to power 0, h raised to power 1, this differentiate, if we differentiate it, then this becomes h raised to power 1 minus 1, okay, and this old one would come here, okay, so this just becomes 1, okay, so this h would just vanish, and that's what we did here. Plus, now we'll differentiate with respect to r. So we have to do that too, because as we said, both r and h are varying. So we have to differentiate with respect to r as well. Of course, that comes out to be 2 by 3 pi. This r will just become r. H will remain as is. Okay. But the problem is we are doing the differentiation with respect to h. We are not differentiating with respect to r. So by chain rule, we will have an additional term here, which is dr by dh. What does it say? It says that I have my volume, the rate of change of volume with respect to height has two components. First is the rate of change of volume with respect to height itself, which is very simple. As I change the height, how does the volume change? The second component, this component, is the change with respect to r. So first we have computed the change with respect to r directly. This is the change. And then how does r change with respect to h? We have multiplied it with that term, and this gives us the rate of change of the volume with respect to r, where r is then in turn changing with respect to h. Okay, so this is what this complete differentiation, that's what it is signifying in this case, when we have a function of two variables, r and h. The partial differentiation, what it means is, it means, we will first denote the symbolism a little bit. So it is given by this symbol. We call this symbol either del, or we call this symbol partial. Okay, these are the two most common names, and we denote it like this. Okay, by. And in this, what we are trying to say is that we were just assuming that when we are doing partial differentiation of volume with respect to the height h, we are just assuming that for 1 second, for that instant when we are doing the differentiation, the r is not changing with respect to h. So we have just ignoring the change of r with respect to h. We have just assumed it to be constant. Okay, so we have just assumed that this will be equal to 0, and that This of course means that we are just assuming that this r has become a constant, and therefore the partial differentiation with respect to h would just come out to be pi r square. See, the thing is, although v is a function of both r and h, that is given, okay, so it's a function in 3 dimensions. It's a function of both r and h, but for the purposes of doing this partial differentiation, just calculating this del v by del h, we have assumed for 1 second that the r is not changing, it has become constant, and that's why we can write this. We have to just make sure that this symbolism, this partial symbol, instead of writing just complete d, is to ensure that we understand that although v is a function of both r and h, we have assumed for 1 second, for the purposes of doing this differentiation, we just assume that r is not changing, it is not constant, and that's why we replace this symbol d with delta. Okay? It's as simple as that. Now the same other way around, if we do it, if we do del v by del r, in that case we assume that this h is not changing, it is constant. So we can simply write it is 1 by 3 pi, and this h is also assumed to be constant. And of course, we differentiate this, so this becomes 2r, and this comes out to be 2 by 3 pi r h. Okay, so very simple. Okay, so concept is very simple, and that's why we have, if you know derivative, then you should be able to use the partial derivatives as well, because the concept is very simple. Now, if we understand the same thing in the terms of geometry, what does it mean? So here is a function z, which is a function of both x and y. Okay, so when we are saying that we are differentiating x, when we are calculating del z by del x, partial differentiation of z with respect to x, we are only doing it with respect to x. For that very instant, for that 1 second, we are assuming that this y is constant. So what does that mean? It means that we have taken a snapshot of this function. Okay, so in this is the z axis. This, which is coming outside, is the x axis, and this one right here, okay, this axis right here, which is going like this, is the y axis. So what we have done when we are calculating this del z by del x, we have just assumed that this y remains constant, which is this plane. So y remains constant along this plane, and we have taken the snapshot of this z with respect to x only. How does z change with x? We have just assumed in this plane, this blue colored plane, we are assuming that the y is actually constant. So the only thing changing along this plane is x. And when we are doing this del z by del x, what we are saying is that assume y is constant for a second, take a snapshot of this x, how does it change with z, and that we have drawn again here. So of course, as you can see, it's a parabola. That's what we would have expected anyways. And then from this snapshot of x, then we can compute how does the partial derivative of z change with x. So this comes out to be 2x. Okay, that is what the differentiation, the slope of this parabola would be at each of the points. And then if you plug in the values, you can find out the actual values. You plug in the various values of x, y, z, then you can find out the actual values of del z by del x. So the idea of partial derivative is that we are taking the snapshot of the function with respect to only one variable while holding the other one constant. So in this case, we have held the y constant at y equal to 0 along this plane, and we have taken the snapshot of only the variation of z with respect to x, and then we have found out the differentiation of that. And of course, the differentiation of that at particular point, for example, this would give me the tangent. That's what the normal meaning of derivative is, would give me the tangent at this point, for example. So this is what partial derivative is. In this next class, we would just understand, we'll just use this partial derivative, we'll apply it to one of the physics problems, which is the propagation of errors. Thank you.